Hi, I'm Ahalya Prabhakar, and I'm part of the LASA lab at EPFL. And today I'm going to talk about our work on credit assignment safety learning from human demonstrations. So our goal in this work is to be able to learn safety guarantees through user interactions in order to ensure safe task performance. And by this, I mean that given a demonstration set with both successful and failure demonstrations, we want to be able to extract the safe and unsafe regions of the demonstration set such that the failures that were experienced are avoided in the future. Importantly, we want a method that does not require users to go through and label specific unsafe states or keyframes from the demonstrations. In addition, we want to allow for user-specific safety functions that accommodates user-specific safety preferences for balancing task performance and safety. To do so, we propose an algorithm to learn a control barrier function commonly used in safety critical control from the demonstration set that is then used as a real-time safety control filter. So, given a set of demonstrations consisting of trajectories and their corresponding reward signals, we define a constraint minimization problem to learn the control barrier function h of x. In addition, we define the constraints such that for safe demonstrations, h of x is positive above the reward threshold r safe. And for unsafe demonstrations, h of x is below the reward threshold r unsafe. And for semi-safe demonstrations, which are demonstrations that are successful but too unsafe for users' preferences, we impose that h of x is greater than the reward threshold r semi-safe, and that h of x satisfies Lipschitz continuity and set invariance. So our main requirements are that for all successful demonstrations, which includes both the safe and semi-safe demonstrations, the reward signals are greater than or equal to 0. For all unsafe demonstrations, the reward signal must be less than 0. Importantly, the reward value applies to the entire demonstration, not just the region that is unsafe. The goal of the credit assignment algorithm is to learn and extract which portions of the demonstration are unsafe. To do so, we introduce slack variables in the failure constraints that enables credit assignment learning by extracting which portions of the fail trajectory cause the failure. By allowing slack in the failure constraints, we can still label the safe parts of the failure demonstrations, which overlap with other safe demonstrations, as safe. Here we show the results of a preliminary example where the goal is to reach a target location while avoiding an obstacle. The reward signals for the safe and semi-safe demonstrations are defined based on the minimum distance it reaches to the obstacle. All unsafe demonstrations have a reward of negative 0.5. The method is able to extract the unsafe regions of the space directly from the demonstrations. Importantly, the credit assignment algorithm is able to extract which parts of the failure demonstrations were causing the failure and not mislabeling safe parts of those demonstrations as unsafe. So overall, we develop a credit assignment method that extracts the failure states from the failed demonstrations without requiring human labeling or pre-specified knowledge of unsafe regions. In the future, we plan to run experiments with an assistive wheelchair robot Quolo from our lab to learn user-specific safety functions for navigation. In addition, we plan to develop and extend the method for more complex tasks and state spaces. Thank you so much.